Hi everyone. Let me check my audio levels. They look good. Let me see how many people are in the chat. Only two. Well, that's all right. We can go ahead and start. Uh, I'm going to continue just doing some problems today. These problems are supposed to help you with your assignment. The problem that we did last time was a block on an inclined plane sliding downhill. It was a single block. This time today we're going to do two problems, and they're both going to include two blocks. Okay, and well, let's just start. All right, and then if you have any questions about the assignment, I should have some time left over at the end of this class. You can ask in the chat, or if you like, I mean, always on the Google Hangouts in the evening. All right, so let's start. My first question here, part A, is I have a 13 kilogram box on a flat table with a coefficient of kinetic friction of 0.25, okay? And it is attached by a string to a 6 kilogram box dangling off the end, okay? And what is the acceleration of the system, all right? So kinetic friction means it's moving, and I'm telling you that I want the acceleration. So you're in a situation where the 6 kilogram that's dangling off at the end is going to be dragging the 13 kilogram across the tabletop. All right, so as usual, begin by drawing a diagram, and then do that in two steps. The first step is draw what you would see physically, and then the second step is to add in the forces. Okay, so here we go. We're going to switch to my other whiteboard, and let me see here. All right, looks pretty good so far. I'm just looking at the various levels here to make sure that everything is working. Okay, all right, so here we go. We got a flat table. Whoops, let's do this in black. Flat tabletop like this. Okay, and on top of the tabletop, I said I have a 13 kilogram box. There it is, like that. And then dangling off of the end, I have a 6 kilogram box. There it is. Okay, and they're attached by a string. There's my string, okay, and it goes around a pulley. I didn't say that in the problem, but um, usually I'm more careful when I do these, when I write the English for these problems, like on a test or whatever. But since we're doing these together, I didn't mention the pulley, but it's there, okay. It keeps the string, going over the table like that. And that's your first step. Okay, so what you should see there is like what you would see in the lab. All right, the next thing is there are two masses, and so we have to actually do two free body diagrams, one for this one and another one for that one. Okay, and free body diagram means identify all the forces. All right, I always like starting with gravity. And so let's start with the 13 kilogram box. There's no reason to do, let me write that up here. This is the 13 kilogram. Okay, there's no reason to start with one over the other, 6 or the 13. But let's start with the 13 here. Okay, and there's gravity, and gravity is acting straight downhill like that. Okay, and you calculate gravity by doing mg. All right, like that. There are two m's, and so you say, well, which m? And so if we call this one m1, then this is m1 here like that. Whoops, let's fix that up. Okay, like that. All right, and m is 13. G is 9.8, but we always round off to 10, like that. And so we get 130 newtons. There we go, 130 newtons. All right, so there's your first force, the force of gravity acting straight down. So you don't have to break it up into a parallel and perpendicular component because the table isn't it's not inclined. Okay, that's actually my next problem. But right now, I've got a flat tabletop, gravity straight down. It's purely perpendicular to the surface of the table. All right. Okay, so now what? Well, the next force I like to do is the normal force, okay? And so the normal force is straight up here like that, okay? And that's Fn, all right? Normal means perpendicular to the touching surfaces. Here's the normal, here's the two surfaces that are touching, and normal means perpendicular to that, so it's straight up like that, okay? So there's your second force, and we'll associate numbers with these forces in a minute. Let's first identify them all, okay? And the next force I like to look at is friction. And so for friction, we have to say, well, which way is this going to move? Like the whole system going to move? Okay, well, the 6 kilogram mass, I mean, it wants to accelerate down like that. Okay, and so obviously the 13 kilogram wants to accelerate like that. Okay, and these two accelerations are actually identical to one another. And the reason is because the string, we're assuming a string which is not stretchy. Okay, and that means, if the 6 kilogram drops by 1 centimeter, then the 13 kilogram moves 1 centimeter to the right, and so on. And so these two masses, they're moving in sync with one another. Okay, and so if one is accelerating down with an acceleration of a, the other one is accelerating to the right with an acceleration of a. So they're the same acceleration. If they're not the same, then what I do is I usually put a subscript on them. I say this is A1 and A2, indicating that they're different, okay? But they're not different. They're the same for the reasons that I just said, okay? The masses are different, so I'll call this one M1 and this one M2, okay? But the accelerations are the same. So whenever they're the same, don't overname them, okay? So, all right, now, why did I point out that the acceleration was this way? Because I was starting to talk about the force of friction, and to answer the question, what direction is the force of friction in, you have to say, well, which way is this thing going to be moving? So if it's going to be accelerating to the right, it's going to be moving to the right. The force of friction has to be to the left like that, okay? And so here we go. There's our force of friction like that. All right. So we got three forces identified, and you ask, well, is there any other force? And if force is a push or a pull, is there anything else pulling or pushing on this thing? Yeah, the string, okay? And so the string has a tension associated with it, and it's pulling which way? To the right. And so there we go. There's the force of tension. All right. So there are the four forces that are acting on that box. And if you think about it, you say, is there anything else pushing or pulling on this thing? No, that's it. It's just those four. All right. Now we could put numbers on these, but let's not do that quite yet. Let's go on to the next one and identify what forces are acting on it. And so on the 6 kilogram, there's a force of gravity down, like that. And it's equal to mg, but this is now m2. So m2g. M is 6, G is 10, and so that gives you 60 newtons. It weighs 60 newtons. All right. And is there any other force acting on it? Yeah, the tension up. And so we'll draw it here, Ft, like this. Okay. And notice that I called this one Ft, and I also called that one Ft. And that's because they have to be equal to one another. Okay, and you might say, well, why are they equal to one another? Well, ultimately the answer is Newton's third law. Okay, Newton's third law. Now, Newton's third law technically says that if one object is pulled in one direction by a second object, then that second object is pulled by the first one in the opposite direction with the same force. Equal magnitude, opposite direction, okay? And these two, they're equal in magnitude. That's why I wrote Ft, but they're not equal, they're not opposite direction. And you go, well, wait a minute, is this really the third law? Because this Ft right here is to the right, this one is up, and up is not in the opposite direction to the right. And so what's going on there? And to be honest, even in the pre-recorded lecture, I did not do a full analysis. This is what's going on. It's that pulley. The pulley changes the direction, okay? So it is the third law, but to do a proper analysis, you have to bring in the pulley, and it's tedious, and so I didn't do it in the pre-recorded lecture, and I'm not going to do it now. It's just sufficient to realize that these two are equal to one another because of Newton's third law. Okay, let me erase this. Okay, so there we go. Those are the only two forces that are acting on the 6 kilogram mass. Okay, so what are the steps again? Draw the diagram. Identify the forces on each of the masses. How many masses do we have here? 2. Identify all the forces on each of the masses, okay? Of the 2 masses. All right, let me see if there's any questions. Okay, good. We've got 4 viewers right now. All right, now we can start to see if we can assign values to any of these forces. Well, we already have for the weight of the 13 kilogram box, we know that it's 130 newtons. But let's go through the other forces and see if we can figure out how big they are. Okay, so let's take a look at the normal force next. So I like going gravity first, then normal, then friction, and then any others last. Okay, so if we go through this, we say, okay, let's look at the normal force here. Do we have a number for it? And the normal force, it competes with gravity straight down. Okay, the two are pulling in opposite directions. All right, and you should ask yourself, well, which one's going to win? Well, if the normal force wins, that is, if the normal force is bigger than the 130 newtons, say it's 131 newtons, well, that means that there's more force up than down. That means that the box would lift off the table, and that's not happening. Okay. What if this 130 newtons is beating the normal force? Say the normal force is 129. Well, then gravity down would win, and the box would like dig into the table, and that's not happening. So Fn can't be bigger and it can't be smaller than 130. It's got to equal 130. Okay? And there you go. That's actually Newton's first law that says that if there's no acceleration, and there is no acceleration up or down, if there's no acceleration, then the net force must be zero. That doesn't mean the net force perpendicular, or sorry, along the tabletop, parallel to the tabletop is zero. It's just that the forces perpendicular to the tabletop have to add up to zero because there's no acceleration perpendicular to the tabletop. Okay, so great. Now we have the normal force, and it has to equal gravity for the reasons I just said. Okay, let's look at the frictional force next. And that one, this is kinetic friction. And for kinetic friction, you can use this formula equals. The coefficient of kinetic friction is given this symbol right here. That's a mu. It's the Greek letter m. Okay, mu subscript k. Mu with an s, that's static friction. The formula is very different. In fact, it's not really a formula. It's an inequality. Okay, and we'll do a problem with that next. Okay, but right now we're doing this one, and it's kinetic friction multiplied by Fn. Okay, so the force of kinetic friction is equal to mu k times Fn. All right, and this should make intuitive sense. Why? Because Fn is how hard the two surfaces are pushing against one another. The harder the two surfaces push, the more friction you're going to get. Like the friction is like the two surfaces locking together. The harder they press against one another, the more they're going to lock, the more friction you get. Okay, so mu k is like what percentage of Fn is FF. Okay, and if you go back to the problem, the English, mu k is 0.25. All right, so it's like 25%. And do we have Fn? Now we do. Okay, we reasoned that Fn is 130 newtons, like this. And if you work that out, let me see, I've worked it out somewhere. It's probably easier that I just redo it. It's 130 multiplied by 0.25. It's 32.5. Okay, so 32.5 newtons. Okay. So great. Now we have three of the four forces. We've got Fn here. Sorry, mg. We've got Fn, and we've got the force of friction. What about Ft? Do we know its value? Not really. We don't know its value. Okay. All we can say is that Ft has to be bigger than FF. It has to be bigger than the 32.5. Why? Because if it isn't, then this thing wouldn't be moving to the right, okay? And it is. It's accelerating to the right. And in order for it to accelerate to the right, Ft has to be bigger than FF. In other words, Ft has to be bigger than 32.5. Okay, so what do? Well, you have to work with the problem not knowing what Ft is equal to at this point, all right? So that's as far as we can go identifying the value of all the forces for M1. Let's take a look at M2. Okay, so M2, we already identified its weight, 60 newtons. What about Ft? We don't know it. Okay, we don't know it for the same reasons we didn't know it over here. We don't know it over here. All we can say is that Ft here has to be less than 60. Why? If it were greater than 60, this would be accelerating up, okay? And it's not. It's accelerating down, so that 60 has to beat the Ft, whatever the value is. All right? So that's it. That's as far as we can go. All right, let me see if there's any questions. I have to switch windows when I do that. All right, good. Let's go on. And let me switch back to the other whiteboard. So let me just write down what we found so far. All right. So we found that the parallel component, oh, not parallel, so the weight of M1, 13 kilograms, like this. We found that the weight M1G was equal to 130 newtons. We found that the normal force was equal to 130 newtons. Okay. We found that the frictional force was equal to 32.5 newtons. Okay, that was that mu k times Fn. And for Ft, we don't know. We don't know what Ft is. Okay, so That's that one. And then for M2, we found that its weight, M2G, was equal to 60 newtons. And FT, what was that equal to? We don't know. Okay? So for the same reason we didn't know FT here, we don't know FT there. All right. And at this point, you go, now what? Well, don't lose sight of what I'm asking you to calculate. I'm asking you to calculate the acceleration of the system. Okay, I guess I should put a question mark at the end here. All right. And you go, well, we've been working with all these forces. Is there a relationship between forces and acceleration? And the answer is yes. Okay. The whole point of analyzing these forces is so that you can get Fnet. And there's an Fnet for each of them. There's an Fnet for M1 and there's an Fnet for M2. Okay. And the reason we want Fnet, that is add up all the forces, is because Fnet is going to equal ma, the acceleration, and that's how we'll get the acceleration. Okay, so Fnet, add up all the forces as vectors. Let's go back to the diagram and take a look. Okay, so we're looking now at the 13 kilogram first, and you take a look here and you say, okay, what do all the forces add up to? All right, and you'll see that this 130 here will cancel that 130 there. Okay, it's 130 newtons up and 130 newtons down, and they cancel. They had to. We already said why. That's because there's no acceleration up or down. All right, and then you say, well, what about this FT and this FF? How do they contribute? Well, FT, it's the one that's winning. It's bigger. So the net force is going to be this FT minus this FF, which is trying to pull it back the other way. Okay, so FT is to the right, FF is to the left. The net force is going to be FT to the right minus the FF to the left. Okay, it's kind of like that FF is like trying to decrease FT. Okay, because it's pulling in the opposite direction. If they were both pulling in the same direction, they would add up. But because they're pulling in opposite direction, they subtract. All right, and so back to the other screen here. All right, so here Fnet, what's it going to equal? Well, you know, this one is out of the picture, right? And this one is also out of the picture because they canceled against one another. It's just these two. And it was FT that was the bigger of the two. And it was competing against FF. All right? And there you go. Okay. And we could even say here, if you like, you could say FF was to the left. And FT, we don't know its value, but we do know that it's to the right. Whoops. And FT beats FF, and so it's going to be FT minus that 32.5, also to the right, whatever that number turns out to be. Now, we can't go any further because I just don't know FT. But the reason we got Fnet, I said it a minute ago, it's because of Newton's second law. We want to make use of the second law. And the second law says that Fnet is equal to ma, like that. Okay. Now, m here is actually m1. And so I'm going to say M1 because I don't want to confuse it with this other M2. And I forgot to put what the value of M2 is. 6 kilograms. Okay. All right. So over here, because we're talking about the 13 kilogram box, we want to put 13 in there. Okay. So now what do you do with this? All right. What do you do with that? For Fnet, you can put in that. We don't have a number, and there's nothing you can do about it at this point. So you just carry the FT along. All right, just carry the FT along. And what's that got to equal? That's got to equal, for M1, let's substitute in 13. And for A, we don't know that either. And so there you go. There's our first equation. Okay, we can't go any further because there's two unknowns here. We don't know FT and we don't know A. We want to calculate A. And if we knew FT, we could, but we don't, and can't pretend that you do. Like, you're not going to get it. There's no amount of examining box number 1 that'll tell you what FT is. Okay, so let's go on to M2. There we have Fnet is equal to MA as well, and M here is M2, okay, because we're talking about the second mass. All right, and let's see if we can figure this out from the diagram. Okay, so if we go back to that diagram and take a look, so now we're looking at this box right here. We have 60. Whoa, what did I just do? There we go, undo. Okay, there's 60 newtons down and there's FT up. The 60 newtons is winning. So the net force, when you add them together, it's going to be 60 minus the Ft, which is trying to pull it up, okay? The 60 newtons down wins. The Ft decreases it because it's pulling up, okay? And so over here, for Fnet, we're going to write Fnet is going to equal 60 minus Ft, okay? So again, 60 newtons down, that's the one that's winning, minus Ft, if you remember from the diagram, that was up. Okay, so the Ft tries to decrease it from the 60 newtons. It doesn't succeed in decreasing it enough that it, will accelerate it up, but it decreases it to some degree. Okay, M2 is going to be 6 and A, like that. All right, and you take a look at this equation, you go, oh, I can't solve that one either. Right, you can't, because there's two unknowns, but they're the same two unknowns as this one. And so this becomes our equation 2. Okay, now I don't know if you've studied this in math, but whenever you have two equations and the same two unknowns, you can substitute one into the other and solve. Okay, you don't even have to do anything that sophisticated. All you have to do with these problems, and it doesn't work in general, but it works for these type of problems. Okay, so feel free to use it. Use this technique is that if you put the two equations one on top of the other like that, if you add the left-hand side of one to the left-hand side of the other, that's going to equal the right-hand side of this one plus the right-hand side of that one. Okay, and so let's do that, see what happens. We have Ft here plus 60 minus Ft, like that. That's going to equal 13A plus 6A, like that. And there we go. So again, the left-hand side was the sum of these two, and the right-hand side here is the sum of these two. Okay, and I think you can see how that preserves the equality. All right. Now the reason it works in these problems is because in one of them Ft comes in positive, and the other one Ft comes in negative. Okay, so Ft positive and Ft negative there, they cancel against one another, like that. All right, so those two cancel. And so what you wind up getting is 92 point, oh, no, what are you going to get? You're going to get 27.5. I was about to add them, I don't know why. So 27.5 is equal to 19 times A, like that. And that's going to equal, that I got to do on my calculator. What do I have here? 27.5 divided by 19 is 1.45 meters per second squared. Okay, and there you go. There's the answer. Okay, so let's switch back to the diagram and draw it in there. Okay, so it's 1.45. So I actually have the acceleration there already, but now we can put in a number. This acceleration down here is, oh, let me use red. This is going to equal 1.45 meters per second squared, and that's accelerating down. And same with this one, it's going to be the same as that one. Okay, and it's accelerating to the right. Okay, so there you go. Now in any of these problems, always ask yourself, does that make sense? Does it make sense that it's 1.45? Well, I mean, like, you might not be able to guess the number, but you can at least, kind of say to yourself or kind of reason that it's right. Like if you've gotten a number bigger than 10, that would have been wrong, because 10, that's like G. I mean, I know technically it's 9.8, but we've been rounding off to 10 meters per second squared. Okay, that's free fall. Okay, that's like if I cut the string here, this thing would fall at 10. Okay, well, I mean, this 6 kilogram mass, I mean, it's trying to fall, but it's pulling this entire 13 kilogram mass in addition to friction. And so, yeah, you're not going to get 10 meters per second squared down. You're going to get something considerably less. It can't be 0, otherwise the problem, you would have no motion at all. It wouldn't be kinetic friction at all. So yeah, 1.45 makes sense. Okay, like in my questions are always multiple choice. And like in one of the multiple choices, you're going to get like answer number A, like 29 meters per second squared. Okay, like you don't even have to think about it. That's just wrong. Why is it wrong? Because it can't be bigger than 10, okay? There's no way you're going to attach a system like that and expect that it suddenly falls faster than if it were just free falling. Okay, so just like look at your answers and make sure they make sense. Okay, so all right, well that's 2A. Let me see if there's any questions in the chat. All right, everyone okay? Let me even type it in there. All right, if there are no problems, let me continue with part B of the problem. Part B is actually easier. Okay, it's static friction. Okay, so I say repeat. In other words, you have the same system as part A. Okay, but this time the system doesn't move. And by the way, these questions are a little bit vague, but that's okay. We're doing them together on a test or on your assignment. I try to be as clear as possible as I can be with my questions. Okay, so basically, let's do the same problem again, but this time there's no acceleration. A is 0. Now, in these kinds of problems, it's almost like you do them in reverse. That is where you have static. And what I mean by that is that here we concluded with A, but here we know what A is right from the beginning. Okay, it's 0 meters per second squared. Okay, now if the acceleration is 0, what does that tell you? That tells you that Fnet must equal 0 for both of the boxes. Okay, and what does that tell you? It tells you that the vector sum of all the forces is 0. All the forces have to cancel on both of the boxes. That makes life a lot easier because you know how like we balance the forces and we say, okay, there's no acceleration, so we balance these two forces. That's going to happen with all of our forces here. They're all going to balance and so that the net force is equal to 0. Okay, so let's switch back to our whiteboard, and this is a mess. So we're going to start over, and we should start over no matter what because it is a different problem. Even though it's similar, you might confuse one thing from another. Like you might take the force of friction from one and confuse it for the force of friction in the other one, and that's wrong. And the reason it's wrong is because it's a different, friction. It's not static. It's not kinetic. It's static. Okay, so it doesn't take long to redraw this. Let's just quickly redraw it. There's our table. There's the 13 kilogram mass here like that, and here's the 6 kilogram dangling off the end. And here's a string that comes around like this. And here's that pulley that's holding the string in place. All right. And there it is. That's what you would see if you walked into the lab. That's the first step. Okay. The second step is to identify all the forces. And so we'll start with the 13 kilogram mass. There's gravity down. And we know how big it is. It's 130. Why? There's nothing different from the previous one. Some of the things are going to be different, some of them aren't. The weight of this box isn't going to be different. Why? Because it's mg, and m is 13, g is 10, and so the total is 130. Okay? Or the product is 130. Okay. Next, there's a normal force up like that. Okay? We'll give it a value in a minute. There's a frictional force. And even though the system isn't moving, it would like to move to the right. Okay, if there were no friction and move to the right, so what's holding it back is static friction, and it would have to be holding it back to the left like that. Okay, so here's our force of static friction. Okay, and you go, is there any other force? Yeah, there's the string pulling it this way, and so there's tension like that. Okay. All right, let's see if we can identify any of these values. Well, we already identified one. We already found that the weight of this thing is 130 newtons. What about the normal force? Well, the normal force has to exactly cancel the 130 newtons, okay? For the reasons I mentioned above. Otherwise, it'd be either accelerating up or accelerating down, and it's not accelerating up or down, okay? And so this has to cancel, so this is 130 newtons, like that. And you say the force of friction, you might be tempted to write this. You might be tempted to write that. And if you did, you would be going down the wrong path. And that's because it's not an equality, it's an inequality. Okay? And because it's an inequality, you really can't use this formula to determine the value of Fs. Okay? And so this whole approach doesn't work. Okay? I'll show you how to get Fs in a minute. We will use this formula, but not right now. Not not to calculate Fs. We're going to use this formula to calculate mu s later. Okay, so let me rub this all off. All right, we don't know Fs and we don't know Ft yet. Okay, so that's as far as we can go with the 13 kilogram box. Let's look at the 6. There's gravity pulling it down, and because its mass is still 6 kilograms, its weight is still 60 newtons. Okay, and what about tension? There's tension up like that. That's Ft. And this value of Ft is the same as that value of Ft because Newton's third law. Okay, with the pulley. All right, now what? Okay, let's see if we can identify all the forces here. Well, we got one, 60 newtons, and guess what? This one must also be what? 60 newtons. Why? What's the acceleration this time? The acceleration is 0. And if the acceleration is 0, the net force must be 0. And if the net force is 0, that means that all the forces have to cancel. So this force up has to cancel that force down. Okay? So 60 newtons up cancels 60 newtons down. All right? So great. We've actually been able to find the tension without having to set up like 2 equations and 2 unknowns. All right? Now, if this is 60 newtons, then guess what that one's equal to? It's also 60 newtons. Okay? And now we have 130 up, 130 down. Those cancel. We've got 60 newtons to the right. And so how many newtons do we have to the left? Well, these two have to cancel. And so guess what? This one has to equal 60 newtons. All right? Because 60 newtons to the left needs to cancel 60 newtons to the right. Okay? And look at that, without having to use any equations at all. All right? We were able to find all of the forces on this system. And really what makes this a much simpler problem, the static problems are simple precisely because of that. Okay? So there's nothing more to do on this diagram. Now we can go back to, whoops, I don't know why I did that. Let me just write in my Newton again. Okay, can go back to our other whiteboard here like this, and we can go ahead and write down what we know. All right, so we know that let's just concentrate on the M1. Okay, the 13 kilogram box. We know that the force of gravity, M1G, was 130 newtons. We know that the normal force, that was also 130 newtons. And we know that the tension was 60 newtons. And the force of static friction was also 60 newtons. Okay? Now, what did I ask for? I said find the coefficient of static friction. So for the coefficient of static friction, this is, I don't have that symbol mu available, so I'll just write it out. This is where that inequality comes in place. The coefficient of static friction, I can't tell you what it's equal to. Like, I don't have an equation. I have an inequality. Okay? You might remember this, well, from the pre-recorded lectures. Okay, so it's an inequality. So we don't actually, even though I say find the coefficient of static friction, a better way to say it is find the range for the coefficient of static friction, because I can't tell you from the information I gave you exactly what that value is. All I can tell you is the range. Okay, and that coefficient of static friction has to be bigger than Fs divided by Fn. Okay, and Fs is 60 newtons, like that. And Fn is 130 newtons, like that. And so that turns out to be 60 divided by 130. Turns out to be 0.46. Okay, so there you go. What is the actual value of the coefficient of static friction? Like I said, I don't know. All I know is that it has to be bigger than 0.46. It could be 1, it could be 2, it could be 10, it could be a million. All right, as long as it's bigger than 0.46, it will not the system will not budge. Okay, if it's less than 0.46, say it's zero point 0.4, well then we're no longer going to be in a situation of static. Okay, what will happen is that it'll break free and it'll start to move. All right, so there we go. That's how you do a problem with static friction. All right, let me take a look in the chat here. All right, 5 people are watching and no questions, so I assume that I can go ahead with question number 3. All right. So question number 3, you could see it there. It's actually like question number 2. It's the same setup, but I've actually got the 13 kilogram on an inclined plane. Okay. Now the way I wrote it is ambiguous. It's not clear which way the incline goes. It could go one way or the other way. Okay. But I could add a little bit of English here, just like I did in the assignment. I said repeat this, but the 13 kilogram box is not on a flat table, but on a inclined plane. The 6 kilogram box is trying to pull the 13 kilogram box uphill. Okay, like that. All right, I think that statement kind of makes it clear that that the situation looks like this. Let me actually just draw it. Okay, and so where are we here? Let me create another whiteboard. There we go, like that. The situation is actually like this. Oh, let me do it in black. All right, it's actually like that. Okay, where you have a box here and that box there. The other possibility, let me actually rub all this out. I'll do it again. The other possibility is like it's inclined, but like which way is it inclined? Is it inclined like that? But if it were like this, okay, with the 6 kilogram like that, and then the cord going like that, then the 6 kilogram isn't trying to pull it uphill, it's trying to pull it downhill. Okay, so that's why that extra little sentence in there makes a difference. Okay, so let me rub this all off and do it again. Okay, so what's our situation? We have this inclined plane. It's actually like a table like this, and it is inclined at 30 degrees. All right, one of my favorite angles, because sine of 30 degrees is a half. Okay, here's my 13 kilogram box like this, and here's a 6 kilogram box here like that. Okay, and there's a string going up here like that and coming down like that, and then there is the pulley here like that. Okay, all right, so now what? Well, now we're going to identify all the forces on each of these. Okay, doesn't matter which one you start with. Just for the heck of it, let's start with the 6 kilogram. Okay, that one's the easier one. I mean, whichever, doesn't matter, like I said. So here we've got gravity acting down, and we know that's going to be 60 newtons. Okay, why? Well, because it's mg. Okay, and m in this case is 6, g is 10, so it's 60 newtons down. There's going to be a force due to the tension up. Okay, so here's our tension up. And how big is it? Ft. And how big is that? Do we know? Nope, not really. We don't know. And the reason we don't know is because we can't say it's 60, because in this case we do have an acceleration. Okay, if we were in a static situation, all right, so the problem said repeat part A, and part A was the kinetic. Okay, so if we were in a static situation, then A would be 0, and then the Ft would have to equal 60. But we're not. We're in a kinetic situation. That is, it's moving, and so Ft has to be less than 60 or greater than 60 so that it's accelerating. Okay, and so there we go. We don't know what's going on or what the value is. All right, let's go back to the other box and see what forces are acting on it. So this time gravity is acting down, but we got to break it up into its x and y components. Okay, so there's a component of gravity acting this way, perpendicular, and then there's one parallel. Okay, now this is like the problem that we did, question number 1 that we did on Tuesday. All right, so whenever you've got an inclined plane, you're going to have to break up your gravity into 2 components. All right, and so the perpendicular component, you just kind of memorize that that's the cosine. If you want to know the justification, like you say, well, why is that cosine and not sine? Okay, well then go back to the pre-recorded lectures and I talk about that. Yeah, basically I have to make a bunch of triangles in here, a bunch of right angle triangles, and it works out. But I don't want to go through that. It's you know, in your interest to just memorize that, okay? And if you plug in the numbers here, by the way, this is M1, okay? If you plug in the numbers here, you get, and I'm just going to give you the answer. So the M1 would be 13 multiplied by 10, that's 130, multiplied by the cosine of 30 degrees. And I'm sure you guys know how to do that. So let me just give you what that answer is. That answer turns out to be 112.6, okay? So 112.6. So over here we will write 112.6 newtons, okay? So ask if you don't know how I did that, but I think it's pretty clear. M1 is 13 times G is 10 times the cosine of 30 degrees, okay? And whatever that works out to, I don't know, but you do it on your calculator and you get 112.6. Well, if this one's the cosine, this other one is the sine. So this one is M1G sine theta, okay? And M1 13 times 10. Sine of 30 degrees is a half. And so this one turns out to be exactly 65 newtons, okay? All right, great. Taking care of gravity. What's next? Normal force. So we usually do normal force next. And a mistake I've seen students make in the past, so don't do this, is to make the normal force go up like that. The reason students do that is because, like in the previous diagram, you know, we had normal force up. And so sometimes students will say, oh, the normal force is up. It's the up force. No, it's not. It's the force which is perpendicular to the surface here. Okay? So this surface is, you know, on a slant, and so perpendicular to that is this way like that, okay? Sorry if you hear my dog, the mailman just dropped something in the box, and my dog is alerting me. All right, so Fn is perpendicular, and so it's also on a slant like that, okay? So I don't think you'll make that mistake, but just in case. All right, so now we got F, all right? Now what? Well, there's tension. And tension is pretty obvious. It's up this way. All right. And it's also equal to, we don't know what it's equal to, but whatever it's equal to, we know that it's these two are the same. Why? Newton's third law. Okay. And again, they're not in opposite directions because of the action of the pulley there. Okay. But they are equal in magnitude. All right. A proper analysis would show that. And now we get to the tricky one, friction. You go, oh no, which way is the friction? So here we have to ask, is the 6 kilogram going to be winning and pulling down like that? In which case this is being dragged uphill like that. Or is the 13 kilogram winning and going like this, and it pulls the 6 kilogram up like that? Okay. Well, you basically guess, and if you get it wrong, then you have to come back, flip the direction of force of friction around, and then do it again, okay? It's not that big a deal, but I'm going to just give you the answer, okay? It's like this. This one's going to accelerate up like that, and this one's going to accelerate down like that, okay? You kind of get an idea that it's going to do that, and here's how you can almost see that. Which two forces are really like the overall forces, like out of all these things, that are really competing? It's this one right here, the 65 pulling this whole system down, you know, to the left. That's competing against this 60 here. Which one's going to win? The 65. Okay, and so that's why the box is actually going to accelerate downhill. Not by a lot, but it will accelerate downhill. Okay, so if the box is accelerating downhill, which way is the force of friction? It is uphill like that. Okay, so there you go. So what's going to happen? This force of friction and this tension, both of them are going to compete with this acceleration downhill. All right? Both of them are going to compete. All right. So we'll do that in a minute, but I just want to show you what's going on. So let me just say that again. Unlike the previous problem, we only had two forces competing. Here we actually have three. We have two of them which are helping one another, the force of friction and the tension force. These two are helping one another. and they're helping to try to slow down this 65 Newton, which is pulling it downhill. Okay, so actually we'll have that 65 minus the other two. All right, we'll do that in a minute, but let's continue a little bit more because there's still some more forces here. We can ask, do we know the values? Do we know the value of the normal force here? Well, there's no acceleration perpendicular to the plane, so this normal force has to cancel the perpendicular component of gravity. Great. That tells you that this normal force is 112.6 newtons, like that. All right. And what about the force of friction? Well, the force of friction, I don't have room here, but maybe I can squeeze it up here. That's going to equal mu k. This time you can use the mu formula here, the mu k times Fn, because it is an equality. So for kinetic friction, it's an equality. For static friction, it's an inequality, and you can't really get an answer out of an inequality. You get a range out of an inequality, not an answer, okay? And so, yeah, we can use it here, and that's going to equal, and I forgot what mu k was equal to. Mu k is equal to, what did I say it was equal to? 0.25, okay? 0.25. And so over here, we get that this is equal to 0.25 multiplied by Fn, 112.6, and that works out to, let me pull up my calculator here, 112.6, oh, 0.6 multiplied by 0.25, I get 28.15, okay? So it's 28.15 newtons. All right. And so if you take a look at this box here, we actually have all the forces except for Ft. We have FF, we just got that 28.15. We've got Fn, 112.6. We've got the parallel component, 65. We've got the perpendicular component, 112. Okay, and that takes care of M1. And for M2, Ft we don't know, and 60 newtons down. All right, so let me take a look here in the chat if everyone is okay. So the only really tricky things with these problems, it's not tricky if there were no friction. If there were no friction, you wouldn't have to worry, because you don't have to worry whether the friction is uphill or downhill. But in these problems where you have like friction, you have to ask, well, do I put the friction uphill or downhill? It depends. Is the box sliding downhill? Then friction is uphill. Or is the box sliding uphill? In which case friction is downhill. If I made that 6 kilogram box into 7 kilogram, then this would be 70. Then it would win, and it would actually be sliding uphill, not downhill. Okay, so just be careful. And you say, well, how will I figure that out? Well, if you look at it and think about this, it's really that 65 pulling it to the down left. Okay, that 65 is really competing against that 60, which is pulling the whole system in the opposite direction. All right, and the 65 wins, so it's actually going to slide downhill. All right, so great. Let's do this problem here, and let me switch to the other screen here like this, and down here. Let me see. Are you seeing that? Yep, you are. Okay. Oh, and we're not on part B. We're on part A. Okay. And so let me just transcribe what we found. I think I can cut and paste from this other. I don't want to waste your time here. All right, there we go. And for the other one, it's, the other one's trivial. All right, did we lose the screen? We did not. Good. Sometimes last class I lost the screen a few times, but I didn't this time. Okay, great. So now what? Well, this is for the M1 equals 13 kilograms. Okay. So here we have the, oh, this is not down. This is, which way was it again? It was uphill. Yeah, whoops. Up. Like that. Okay. All right, good. All right, so we had the parallel component of gravity was 65 newtons downhill. Okay, the perpendicular component was 112.6 newtons. Okay, the normal force had to balance the perpendicular component, so it was also 112.6 newtons. The force of friction was the coefficient of kinetic friction times Fn, and that was like 0.25 times 112.6. That turned out to be 28.15. And the tension we didn't know. Okay, all right, what's next? If you find that you're not sure what's next, that's because this is usually where students get confused and lost. You did this entire analysis in order to get Fnet. That was the whole point of doing this. All right. So once you've got all the forces, even if you don't know the value of one of them, but you've at least identified all the forces and given values the best you can, okay, now you're ready for Fnet. Okay, so for this, I really have to go back to the diagram one more time to make sure we understand what's going on here. So we're adding up all the forces for this box here, okay, and the force. What color should I use here? You know what? Let me use yellow. This force here, oh, we'll cancel that force there, okay? Because we said that they had to, because there's no, that yellow doesn't show up here. Let me just do it in blue. This force here has to cancel that force there, okay? And the reason is because there's no acceleration perpendicular, okay? And then what about parallel? What forces do we have parallel? Well, we have tension, force of friction, and parallel component of gravity. We got 3 of them. Which one is winning? Well, the 65 Newton is winning because the thing is going to slide downhill. So it's going to be 65 minus the force of friction, but minus also the tension. Because both the force of friction and the tension, they're trying to pull it uphill. They're trying to decrease that 65 newtons. So the net force is going to be 65 minus the force of friction minus the tension. Okay? And so I hope that's not confusing. But once again, you say, well, which way is it going to accelerate? Down. Okay, down. That's the one that's winning. It's going to be this one minus the 2 that are competing with it. Those 2 are up. Okay? All right, let's switch back over here. So Fnet is going to be the 65 downhill minus the force of friction up, and that's the 28.15, but minus also the tension up, and we don't know its value. We just don't know the value of Ft. That's okay. You just carry it along as a symbol like that. And so what's this going to equal? This is going to equal what? 37.85, is that right? Let me see here. Yeah, 36. 36.85. Okay. All right, good. Minus Ft, like that. Okay. And why did we want Fnet? Because we wanted Fnet to use it in Fnet is equal to MA, like that. And this isn't M2, it's M1A, like that. All right. And so now we can substitute in. All right. So what do we substitute in for Fnet? Well, we don't have a number, but we have almost a number, everything except for Ft. Okay, so that's all right. There's a variable there, but just carry it along. There it is. For M1, that's 13, and there's A like that. Okay, and you say, can I go further? Nope, that's as far as you can go. Okay, because you just don't know Ft, you don't know A. In fact, A is what you're trying to find. So just like the previous problem, you can't go any further. So what about M2? What can we say about M2? All right, so remember, we're heading towards Fnet. That's kind of our goal in all of this. And so let's go back to the diagram and see if we can get Fnet. And it's pretty easy, actually, because here we have 60 down competing with Ft up. Okay, and so the net force is going to be 60 minus whatever that competition is, minus the Ft. Okay, and so Fnet is going to be just 60 minus Ft. All right, that was easy enough. Okay, so Fnet here is going to equal 60 minus Ft, like that. And why did we do that? Because we want to plug into this equation, but now it's M2. Fnet equals MA. Where am I getting this? Okay, where's that magic coming from? That's Newton's second law. Basically, Newton says, look, if you've got Fnet, just set it equal to MA. Okay? That's what the second law says, all right? And you say, well, how do you know that's true? Well, that's experimentally verifiable. And you're going to do, I think you're going to play with Atwood's machine in the lab. Okay, so, this is actually experimentally verifiable. Okay, so for Fnet, you put in whatever number you have. You don't have a number, but you almost have one, everything except for Ft. That's going to equal, all right, so just aligning the equal sign to show you what I'm substituting. So Fnet gets substituted with this. That's going to equal M2 is going to be substituted with 6. And A we do not know. Okay, so there it is. So A gets substituted with nothing. And there we go, equation number 2. All right, and now what? Well, we've got equation 1. We've got equation 2. Write them one underneath the other. Okay, and you can already see what will happen when you add these. Uh-oh. Not in this case. In this case, actually, my adding the 2 doesn't quite work. I have to subtract the 2. Okay? So it's a little bit different. I hope this doesn't confuse you, but it's because FT was up the plane instead of down the plane. Okay? So here, let me see, make sure I did it right. FT is up the plane. Yeah, that's right. It's right. It's right. FT is up the plane. And here, so here we have the third. Yeah. Okay. It's just a little different. All right. I had to convince myself there. So here, what you want to do is, did I make a mistake? I'm not sure here because it looks like things are not going to work out right. Guys, I think I made a mistake. I'm so sorry about this. Let me just take a look at the diagram again. FT is up, yeah. Okay. I'll switch back. FT is up, okay. There's FF, which is also up. Okay, so those two add together, and that's 65. So it's going to be 65. So let's switch back here. I may have to finish this later. It's funny, I didn't make a mistake in the last class, so what did I do wrong? What did I do wrong? So we have 60 minus FT is equal to 6A, that's right. And here we have 65 minus the force of friction. I know what I did wrong. Ha 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 ha. I know what I did wrong. It won't work with 0.25, okay? It will not work. So almost, let me make a small little modification here, okay? And over here, repeat also the can you see that? No, almost. All right, sorry about that, guys. This is the danger of not solving a problem beforehand. Also, the coefficient of kinetic friction is only 0.025, okay? So let me explain what's going on. I had a coefficient of friction which was too big, and so that's why it wasn't working, because it's not gonna slide downhill. All right, and I assumed that it was, but it's not gonna slide downhill, and so that's why I'm getting a mistake. Okay, so when I went to solve the equations in my head, I noticed that there was a problem. I was going to get a negative acceleration, and that's wrong. Okay, so that's all right. It's not that big a deal. We'll just change that to 0.025, and what that means is that over here, instead of it being 0.25, this is 0.25, and that just moves the decimal over by 1. Okay, now if that moves the decimal over by 1 there, okay, hopefully I'm not going too fast. So in calculating the force of friction, rather than 28.1215, it's going to be 2.815. Over here, this is going to be this number here, like that, 2.815. Okay, and that's going to equal not this number, but 65 minus 2.815. That's going to be this number. Okay, and that means that this equation here will not be that, it will be this. All right, so sorry about that, guys. I don't know, I just wasn't thinking when I was setting up the problem. Okay, so is everyone okay? Did everyone see what the change that I made there? So just to be very clear about what change I made, back to the statement of the problem. Okay, so in the statement of the problem, I'll trace through the change again. The only other thing that two things change. One, the box is on a inclined plane, and also the coefficient of friction is 0.25, 0.025, not 0.25. Okay, now what that changes here from the previous calculation is before I had 0.25 here for the coefficient, it's 0.025 times the normal force, 112.6, and so I get 2.815. Before I had 28.15, now I got 2.815. Okay, so so the rest of the reasoning is the same. It's going to be the parallel component minus the friction minus Ft, but now the friction, like I said, is 2.815. And so when this simplifies, it simplifies to 62.185 minus Ft. So equation number one is 62.185 minus Ft. Okay, now down here, all right, this is not going to be 36, it's going to be 62.185. Notice that it has to be bigger than 60. Okay, that's the fact that the FT was in the same direction wasn't the part that bothered me. What bothered me is that when I did the subtraction, I got a negative number. Okay, but this is correct. Okay, so if everyone's good so far, all right, just um, ask me if you got confused about what happened there. But if everyone's good so far, this is wrong. But there we are. Okay, so far. All right, now what? Now, if you try to add these, it won't quite work out the way that I said that it would before. Now, if I add these, I've got a negative FT here and a negative FT. The problem is that if I add them, what will happen is they'll get negative 2 FT. So what I want to do is subtract the two rather than add them, subtract the two. And it's not that bad. Okay, so basically I'm going to take this here, 62 point minus FT like that. And I'm going to subtract from that one this one. Okay, so does everyone see what I did? So because this is minus FT here and minus FT here, I want them to cancel. I'm actually going to subtract. So I took the 62.182 and minus FT, and I'm subtracting from that the 60 minus FT. Okay, and I put brackets around it so I wouldn't confuse any of the signs. Now if I subtract the top one from the bottom one on the left, I've got to subtract the top one from the bottom one on the right, like that. Okay, so ask me if you're confused about what I did there. Okay, it's just a little different. Before I added the two, because that would cause FT to cancel. Here I'm subtracting the two because that'll cause FT to cancel. Okay, so all right, let me see. Anyone in the chat freaking out? No one's having problems. Good. All right. Well, let me continue then. So right now, what I'm going to get is 62.182 minus FT minus 60 plus FT. Okay, and that's going to equal 13 minus 6 is 7A. Okay. Now, what happened here? So I had 62.182. There it is. Minus FT. There it is. Minus plus 60 is minus 60. Minus FT is plus FT. Okay, and now notice what happens. This negative FT here cancels with that positive FT there. Okay, so ta-da, these cancel, and now I get that 62.182 minus 60 is equal to 7A, and so I get that 2.182 is equal to 7A, and so A is going to be a rather small number, but there it is. So what's that going to equal? 2.182 divided by 7 equals, is that right? Yeah, I guess. Let me see here and just make sure I didn't make a mistake. Just looking back here. I'll scroll back in just a second. Yeah, that makes sense. Yep, it makes sense. Now that's too many decimals, but I just cut and paste from my calculator. So, rounding off to maybe 2 decimals is good enough. Okay, like that. All right. So I apologize for that that little boo-boo there, but it was a quick fix. So, when I set up these problems, I just make up the numbers. and sometimes I'll make up numbers and I'm wrong. Like I've just made up a meaningless number, okay? And I don't realize that until I solve the problem. And so I must have done that when I set up these problems, okay? So, but it was a quick, easy fix, all right? So the acceleration is only 0.31, okay? What was it before? It was like 0.14, was 1.47. But now it makes sense that it's going to be less because there's more competition. You know, that 13 kilogram mass is actually pulling in the opposite direction. Okay, so if everyone's good with that, let's go on to the last one. Okay, so looking in the chat here. All right, good. Let's go on to the last one. So the last one says repeat 2b, but again, this time the box is on a plane inclined at 30 degrees. So which one's 2b? It was basically repeat, but the system doesn't move. In other words, let's just do this problem again with the box on the inclined plane, but it's not moving. This one's much easier than the previous one. The previous one, by the way, is about as hard as they're going to get for you, okay? So this one is much easier, all right? So let's go over to our whiteboard, and this diagram is now a mess. So we'll just create a new whiteboard like that. And let's just redraw everything. It shouldn't take too long. Well, like this. And this angle here is 30 degrees. Okay, here's our block. This one goes over like that. Okay, and we need a pulley like that. Okay. All right, good enough. All right, so let's do the forces. Pick either box, doesn't matter which one's which. You know what, let's start with the 6 kilogram. You'll see why. Because everything will unravel faster with the 6 kilogram. Okay, so let me see if this is working. Okay, so over here, force of gravity first, down, that's M2G. We know that that's 60. Okay, 60 newtons, right? So hopefully you can see why. Basically M2G, M2 is 6, 6 times G is 10, that's 60 newtons. Okay, so this thing weighs 60 newtons. Basically, just think of it this way. You know, if something weighs 6 kilograms, it weighs 10, it has a mass of 6 kilogram, it has 10 times that number for the weight. Okay, so 6 kilograms weighs 60 newtons. All right, now there's the tension up, and I've been doing tension in purple, so here's the tension up like that. And guess what? You can say exactly what the tension is right away. Why? We're in a situation of statics. Okay, so static means that there's no acceleration. If there's no acceleration, all the forces have to cancel. So this one is the only other force there is, and it cancels against that one. So guess what? This has got to equal 60 newtons. Great. Okay. So that takes care of the 6 kilogram box. The other one is the 13 kilogram box. And for gravity, we'll immediately break it up into the two components. So the perpendicular component, mg cosine theta, you plug that all in, you'll get the same number as we did above, 112.6. Okay, 112.6 newtons. And the perpendicular component is 65 newtons. Okay. All right. So nothing changed there, so you'll get the same numbers again. Normal force. Well, the normal force is like that. Okay. And it has to cancel this one. Why? There's no acceleration perpendicular. So the normal force here is also equal to 112.6 newtons. Okay. And what other force is there? Well, there's two others. There's tension uphill, like this. And you say, how big is that one? Well, we know, because the tension is the same throughout the string. So if it's 60 newtons over here, it is 60 newtons over here. Okay? Finally, friction. What is it? Well, take a look here. This force has to cancel that force. We argued why it does. Okay? The net force on this whole system here, the whole 13 kilogram box, that has to be 0. We've got 65 newtons downhill and only 60 newtons uphill, so that's unbalanced. So guess what? The force of friction, which way is it? It's uphill. And how big is it? Force of static friction, that has to be your 5 newtons. Why? Because now we have the tension and the friction uphill adding up together to 65, and we've got the gravity parallel component downhill adding up to 65. Okay? And so that's how you can determine the force of static friction. So the force of static friction, you don't use this formula here to find it. That's not how you do it. Okay? Okay, that's wrong. What you do is you simply say, okay, what does the friction have to be such that it doesn't move? And so you say, well, if this is only 60 and that's 65, then it has to be 5 to make up for it. Okay? So you'll notice that once again, like in the previous static friction problem, we know all the numbers. We have all the values for our forces. Okay, so let me switch back over here, and let's calculate the forces, the coefficient of static friction. It's given by this formula right here. So let me cut and paste it from above. And basically, it's the force of static friction, which we found was 5 newtons, and the normal force, which we said was what was it again? 112.6 newtons, like that. And let's see what that works out to. 5. It's going to be a small number, but there it is. 112. It is what it is. Okay, it turns out to be that number right there. Okay. Oh, there's no units. Sorry, I was about to put newtons there, but there it is. So the coefficient of static friction is bigger than, I don't know what it is, but I know that it has to be bigger than 0.0444. Okay? And that answers that question. By the way, the coefficient of kinetic friction has to be smaller than or equal to the coefficient of kinetic friction. Okay? Well, what did I have when I made my mistake? I said this was 0.25, right? That's how I started the problem. Well, that can't be right, because we know that the coefficient of static here. There we go. The coefficient of kinetic friction here was 0.25. That has to be less than or equal to 0.044. Well, that doesn't work, does it? Okay, 0.444. Okay, because 0.25 is not smaller than that. And so that's another reason why I made a mistake when I put 0.25 there. But 0.025, that is smaller than 0.0444. Okay, and so that's why I knew that this value would work out. Okay, so all right, we're done with the class. I'm just going to switch over here to the chat. If you have any questions about what I just did, or if you have any questions about the assignment, you can ask now. All right. And if you've tried the assignment, you can ask now. If you haven't had a chance to try the assignment, then do it right away, because it's due tomorrow. It's 25 questions long, and that's long enough that you might get stuck on something, and then I don't know, you're running around trying to catch me, and that's not always easy to do, considering that everything is online. Okay, you could try emailing me, and I will answer, but I don't know what my schedule's always like. So the best thing to do is to catch me on my office hours, either tonight or tomorrow night, and tomorrow night will be the last chance you get to ask me questions. Okay, so I'm not seeing any questions in the chat, so let me just say goodbye, and we're done for today. Okay, I hope this was helpful. All right, bye bye.